So we were talking about the four function operations. You can do function addition, subtraction, multiplication, and division. And there's a couple ways you can do it. You can define the function itself. You can look at a graph. You can look at a table for it. Those aren't super interesting, but what is interesting is function composition. Function composition. This is likely something that you have worked with before, function composition. And this involves wrapping one function inside of another. So our vernacular for it is going to be F composed. And so that's supposed to look like a little circle. You know what? Let's F composed. There we go. That looks much better. Of G of X is going to be the function G of X basically inserted into the function F of X. So you read this, F composed of G of X, or you can say F of G of X. F of G of X over here. Okay, what that's going to be is, let me show you an example. Let's say you have two functions. Let's say you got F of X. Let's use a different color. F of X is a simple linear function. Maybe 3x minus 5, slope of 3, y-intercept is 0, negative 5. And let's say that G of X is the function, how about 2x squared plus X? F of G of X, what that says is that we take the G of X function here and we plug it into the function F everywhere we see the variable. And when you plug it in, it's probably a good habit to put parentheses around everything. So it's 3 times, now we're going to insert the G of X function, 2x squared plus X minus 5. And now we simplify that, combine like terms if there are any. We find that we can distribute the 3, so we get 6x squared plus 3x, and then this minus 5 over here didn't have the 3 attached to it, so it's just minus 5. And so this new function we've created, F of G of X, is the original function F with the G of X function basically inserted into it. Again, we can use this with, it looks like fog, something like that. Now, what's really interesting here, what's perhaps far more interesting than that, is if we go the other way. If we go the other way with it, it's going to become something different looking, at least on the surface. We can do F of G of X, but we could also do G of F of X. We can go either way we want. We can put any function we want into any other function we want. So let's actually do that with this f and this g as selected. So let me get rid of some of this, give ourselves some space, bring this up. Choo, 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 choo. Complete with sound effects. Now today's Thursday, and I know that's not the same as Friday, but I'm still excited. I love Thursday. Thursday's great. And guess what, guys? Today is the first day of October. Today's October 1st, and this is just like the happiest time of the year for me. My girlfriend and I were going to spend the entire month of October celebrating Halloween, and we're not like weird people or anything. I like the corny, like, ooh, there's cute ghosts and stuff. I like that kind of side of Halloween. I think it's fun. So I'm really excited for Halloween. But then Christmas is also awesome. Thanksgiving. This is just the best time of the year. Of course, I'm a super optimist. So every time of the year is amazing, but this is just a little bit more amazing. So we're going to go the other way. Now we're going to plug the function f of x into the function g of x everywhere we see the variable. We're going to do g of f of x. And that's like saying, look, f of x is being put into the entire g of x function. That's why there's two parentheses there. It looks a little bit sloppy, maybe, but that's the best way to write it, in my humble opinion. So now the g of x function is like the outer function. So it's going to be 2 times not x squared. Now we're going to put this 3x minus 5 in for x. And again, putting it in parentheses is very smart. And then it's being squared. So 2 some business squared, just like this was 2x squared. Plus, well, here's x again. So now we need to put the 3x minus 5. Bada bing, bada boom. Now, the lazy person inside of all of us, and we all know, even if you're very hardworking, diligent, industrious people, we all know there's a lazy person that every once in a while just says, all right, I'm done. I've done it, right? Yeah, technically you have put f of x into g of x, but there's just kind of an implied mandate that says, okay, but now simplify it, combine like terms. So we've got this thing squared. And of course, it's not just square the 3x, square the 5. No, no, no. We need to do this. We need to FOIL it out. Again, it's entirely implied that we ought to be doing that. And then there's even yet a 2 that has to be multiplied there. And then we're just doing plus 3x minus 5. There's nothing fancy to distribute. You could say you're distributing a positive 1, which doesn't do anything. What I'm saying is I'm justifying the fact that we're just going to drop the parentheses here. Nothing has changed to it. So now we need to FOIL this out. And remember, there's still a big fat 2 we've got to multiply out. It's going to be 3x times 3x, which is going to be 9x squared. 3x times negative 5 minus 15x. Minus yet another 15x. Negative 5 times negative 5 becomes plus 25. And then we still had all this 3x minus 5 business. All right, we're still not done. We still got work to do. We're going to go ahead and combine these like terms. And I normally like to do that on another line here, but we're just going to run out of space. So I'm just going to go ahead and combine them. Minus 15x combines into minus 30x. Ta-da! And so I'm going to merge all this back near each other. And now we'll use black. Orange and black are Halloween colors. We're going to distribute this to very good, very good. And now we're going to combine like terms. The 18x squared is all alone.
Yeah, it would be. You forgot to distribute it too.
On the 25.
On the 25, you're absolutely right. Thank you. You are correct. Thank you very much.
They noticed it, not me.
That's good. That's good. You're paying attention. 5 points to Gryffindor. Now, I don't even know what that's from. I just hear like 10 points to Gryffindor. I hear it like on YouTube videos and stuff. I'm like, what's that from? And people tell me it's from this story about these kids that go to this school and they learn how to do magic or whatever. And the main character is called Harry Potter, but I don't even know what the movies are called. I have no idea. So, anyways, minus 60x plus 3x. That's going to end up being minus 57x. And plus 50 minus 5, plus 45. Now, I do take pride. I usually don't make mistakes, but every once in a while I do. I try my best not to, but no matter what, you can't help it. Sometimes it happens. And so we end up with something like that. That looks a lot different than when we did f of g of x, when we plugged the g of x function into f. So that goes to tell you right off the bat that plugging one thing in one way and then doing it the opposite way is not the same thing. They're completely different processes sometimes. They look nothing alike. So 18x squared minus 57x plus 45, and that's it. That's the final answer. That's g of f of x, and we can all go home. Not literally, you guys can't. All right. So that is kind of the basics behind function composition. We're not going to get too worried about the domain of it because you have to deal with domain and range. You say the domain of the new function is the range of the interior function and blah blah blah. It's just nasty. So we're not going to bother ourselves too horribly much with that. What we will talk about, and this is a favorite talking point because this is actually going to be secretly introducing you to some calculus. Real quick, by show of hands, that I cannot see those hands, but do it anyways. By show of hands, how many of you are daunted or you're afraid of calculus, or you would just assume that calculus is going to be a really hard math class? How many of you? You can be completely honest with me. I'm not going to judge. No judging. Of course, I can't see if you're raising your hands anyways. So, is there a good amount of hands raised?
17 out of the 22.
Okay, that's not bad. So, some of you who, what's that?
They're wrong. It's not that bad.
Exactly. I mean, you're wrong, but in a gentle sense of the word. You're wrong because you simply have not taken calculus, so you don't realize that calculus is actually not as bad as you'd think. The reason most people get tripped up on calculus is because they come in and they're just not absolutely solid in their prerequisite math knowledge. You got to come in knowing, if you've taken pre-calculus, they're going to preach that unit circle, which is related to your trigonometric functions. There's all kinds of little things, tips and tricks. Solving a quadratic should be second nature to you. If you come in with the proper prerequisite knowledge and you're solid and firm in your foundations, calculus is really not that bad. I would even argue that calculus is easier than college algebra sometimes. I'm dead serious. So, don't let it scare you. Just make sure you come in knowing what you know about previous math knowledge and you'll do fine. But what we're going to do is I'm going to lightly introduce you to calculus without calling it calculus. We're going to look at something called the difference quotient for a function f of x. The difference quotient for a function f of x. So the first thing I'll do is I'll just define it. No, that needs to be a straight line. It's going to be f of x plus h minus the original f of x all over the function h, where h is going to be a new variable that we're going to introduce, but we're not going to do much with it. We're just going to assume almost like it was just the variable y or z. We're just going to throw it in there. In calculus, you'll see the interpretation for it. In calculus, you'll go one extra step and you'll have learned by now something called a limit. You'll throw a limit in here, and that will suddenly turn it into the definition of what's called the derivative. And in calculus, the derivative is one of the major concepts of calculus. Just absolutely massive. So let me show you how it works. It's not going to be quite as bad as it looks, and it involves function composition, because we're going to compose with this new kind of fangled thing. So let's compute the difference quotient. And if I'm ever using the term difference quotient, I'm automatically referring back to this thing. Let's compute the difference quotient for a function. Well, let's do our little 3x minus 5 that we had earlier. And we're going to kind of do it in 3 steps. Step 1, I'm just going to compute what this f of x plus h business is, all by itself. And believe it or not, that's actually usually the hardest step. That usually is. So let's see, f of x plus h. So that suggests that everywhere I see my variable in the function, I just pop an x plus h in there and deal with the consequences? Yeah. Where h is just some other variable. Yeah, that's exactly what I'm going to do. Okay, so I guess to simplify this, I would just distribute the 3. Yeah. That's it. Step 1's in the books. Let me give myself a little more space. Okay, and so this is, I hate to use this phrase, but it's almost like fake it till you make it. Just try it out the way you think it ought to go. And you'll see that it really does kind of go that way. Now, step 2, let's do the whole numerator. Let's do this f of x plus h. Too close to the edge of the screen. Let's do f of x plus h minus the original function f of x. Let's do the whole numerator. All right, well, I got f of x plus h as 3x plus 3h minus 5, correct. Now we're going to subtract off the original f function, and we need to put it in parentheses because we need to subtract the entire thing. Let's see if I can even squeeze this all up and give myself even more room. So take the f of x plus h function, subtract the original f of x function of 3x minus 5. Well, this then suggests we distribute the subtraction. Minus 3x plus 5. And you'll see that while it's cumbersome, there's a lot of stuff going on. It's not exactly difficult. We're going to combine like terms. Oh, wait a minute. 3x minus 3x. Ooh, those are going to cancel each other out. And then look, we have minus 5 plus 5. The only business we have left is business involving h. So this is going to end up being just 3h. And now finally, for step 3, we're going to do the whole gosh darn thing. We're going to do f of x plus h minus f of x, which is the thing we just computed, all over h. But wait a minute, this whole numerator here was this 3h. So all we're doing it is dividing it by h. And we're going to see h's cross out. I'll use red to do that. The h's cross out. And I'm just left with 3. And that's correct. That's going to be the answer. Just 3. We did this whole difference quotient business and we ended up with 3. That's pretty cool. Why do we do the difference quotient? Well, like I said, it's related to a very important calculus concept that you will absolutely be visiting in a calculus course should you go on to do that. If not, it's still an interesting application of composition of functions. You can think of it as I composed f with this x plus h business. Now I have to step out of the room for just a moment. I will, as the kids say, BRB. Back to it then, pip pip. All right. So lots of business going on, but it was really, I think, a little bit simpler than it looked, in my humble opinion. Let's try out one more. So if I say just compute the difference quotient, it's clear we want to use that formula. Oh my God. There we go. Compute the difference quotient for, let's do 3x squared minus 7. And you know what? 3 is boring. 3 is so 2019. Let's do negative 4. There we go. Negative 4x squared. All right, Will, I suggest doing the 3-step process. In calculus, it's a 4-step process because you just add one more thing onto all the work you've already done. So step 1, we're going to compute f of x plus h. All right, so let's see, that's going to be negative 4 times the x plus h, but then it gets squared. Remember your composition of functions. Minus 7 is still out here. And you'll now recall, oh, wait a minute, I got to square that. And it's not just x squared plus h squared. No, no, no. If only it's actually this, where you have to FOIL a binomial. How many of you want to hear a really cheesy joke real quick? You guys want to hear a cheesy joke? Oh boy. This one's reaching. I'm just going to tell you now, this one is reaching. Reaching for the stars. All right. So let's say you're just minding your own business and someone comes and asks you out to dinner. Now, you may or may not be going to a restaurant right now because of the pandemic, but whatever. So they ask you out to dinner and you agree. And so you go out and you have a meal with them. Well, usually the person who asked you out, they'll usually offer to buy. That's the whole point. They'll pay for the meal. So, oh boy, you ain't got to buy no meal. You ain't got to buy no meal. Uh, it's not your responsibility in that situation. Buy no meal. All right. Uh, I apologize for that one. That joke has actually been put on the list of banned jokes, simply because it's not very funny. That's all it is. Okay. So we got to foil this one out. I used to have a joke every time I'd mention foil. I would say, well, I'm part of a group that goes to foil conventions where we dress up as famous characters from everything, in tinfoil. We literally would, so you have someone dressed up as Superman in tinfoil or something like that. But they hold the foil con, we call it, in Miami every year, and it's an outdoor event, so it's terrible. You go there and the sun is just in your eyes the entire time. It's shining off everybody. So yeah. And see, this is a little weird because if I was in the room with you and I saw that it got laughs, I would just say, that was a pretty good joke. If it didn't get laughs, I would also say, well, that one's included on the list of banned jokes for not being funny. So I'll just kind of show you the idea behind my humor, and it's not very good. So we got x squared, then we have x times h, and there's really no other way to write that than just plus x times h. There's nothing you can really do about that. Then you come over here and you're going to doing h times x, but thanks to the commutative property, h times x is the same as x times h. Yeah, I guess you could swap them, and that's the way it would look normally. But the reason I'm going to put it back this way is because that implies they're like terms, which they are. And then there's going to be plus h squared. And you close off that parentheses and you still have the minus 7 out there. Now look what you have. You have these things, they're like terms, but there's two variables involved. Josh, how do I deal with that? Just think of it like this. You have one object here, you add them together, you have two of that object. And that object is the x times h. So in order to combine these like terms, we're just going to call that 2xh. So let me space that out here. And there you go. Like terms have been combined. Now all we got to do is we got to distribute this negative 4. Negative 4x squared minus 8xh minus 4h squared, and then just that minus 7 over there. So as you can see, we went from the last one we just did, that 3x minus 5 function, which was just linear. Just going up to a quadratic now actually it increases the overall complexity of it. It causes us to have a lot more steps. Now step 2, let's not use green, let's use blue. Because if I were green, I would die. Now step 2 in the difference quotient is to do f of x plus h. Ugh. Minus f of x. Well, here's f of x plus h down here. And I gotta admit, I'm just gonna do something kind of lazy. There you go. And I wouldn't call it lazy as much as I would call it being smart with your resources and your time. And so now we've got to subtract off the original function, negative 4x squared minus 7. And you're probably starting to notice a pattern. When you do this step, some things are going to fall away. Some things are going to go away, and that's exactly right. That's exactly right. We're going to end up distributing this subtraction here. So this is actually going to become plus 4x squared. Instead of minus 7, it'll become plus 7 once we do the distributing. Well, all right then, Pilgrim. That's good. That's good news because we have negative 4x squared over here, but positive 4x squared over here. And here's that cancellation. It's usually going to happen if your function is relatively simple, but you can compute the difference quotient for anything. Plus 7 minus 7s cancel out. And now all you're left with is negative 8xh minus 4h squared. So finally, step 3 is going to be do the entire difference quotient, which is f of x plus h minus f of x all over h. But we just computed that entire numerator to be negative 8xh minus 4h squared. And now all we got to do is divide that by h. But now we notice something magical is happening. Look, we're dividing by h, and both the things up here have at least an h involved with them. So we're thinking, just like last time, let's see if we can do any cancellation maybe with that h. And guess what? You can. You could factor an h out of the top. There's still a single h attached to that 4 in there, but by writing it this way, we can see those h's cancel. That is exactly what we're going to want. I still need more space. So all you're left with is this business on the inside here. Negative 8x minus 4h. And you're done. You're donezies. That is the final answer for this. In calculus, you'd go the extra step. You'd take the limit as h approaches 0. Because this is a polynomial in h, you would just be able to plug 0 in for h, and all you'd actually be left with is the negative 8x. But that's next level stuff. That's when you get to calculus, you'll deal with something like that. So let's pause for a moment. This is the end of chapter 2. We've just finished it. Do you guys have any questions over this? Any questions for me? All right. If not, then we will continue on. What we're going to do for the rest of class, we are going to start chapter 3 just to kind of get some basics going. But then what we're going to do this next class on Tuesday, we're going to do a review over chapter 2 material. Remember, you're going to have an exam 2 review popping up on MyLabs Plus. That's going to show up there. You can work the review to your heart's content. And so what we'll do on Tuesdays, I will just field any questions you have over chapter 2. I'll even work homework problems if you want. So make sure to get any of those that you want covered kind of queued up. And then we can work some of the review. I'll probably draw some inspiration from the review on Tuesday. Let's get this unpleasant lookingness off the screen. And so Tuesday we'll spend reviewing, and then next Thursday, October the 8th, will be our exam, our MyLabs Plus exam in class. So that is some good news. Good news we will be reviewing. But for the sake of time, we got through it a little quicker than I had originally planned, which is usually a good thing. It's usually you don't have the luxury of that. And let's just say real quick, I think I've mentioned this before. In a high school class, you might, usually you take a class over the course of an entire school year, fall and spring. And I think you guys meet for longer. Each week you get more physical hours in with a specific class. And then I think you have 18-week semesters, 3 6 weeks at a time. So you're meeting for 36 weeks and a little bit longer each of those 36 weeks. Whereas in a college course, it's condensed into a single semester and that's only 15 weeks long. So you have less than half the weeks. And if you think about the time, the fact that you get less time even in a given week, you get somewhere between 2 to 3 times more physical time to take a course in high school than you do in college. And that is not lost on college instructors. We recognize that, and we see that, man, we just don't get a ton of physical time to work this. I mean, everything takes time to really learn it, let it sink into your brain. That's why cramming the night before an exam and not knowing anything, you're not going to do well at all. It's just usually, unless you're a super genius or something, unless you're just lucky or magical. But for most people, you're not going to be able to do that. So that's just a little word of caution, is that in college, things just move at lightning quick speeds. And I mean, even the instructors, we don't get to sit and just talk about things we like, oh, I love talking about this. This is my favorite thing. We don't really have the luxury of that. So the fact that we're actually a little bit ahead is kind of a rare treat that I get. And I will take that as an opportunity to make your eyes roll with my corny jokes. Of course, I'm not actually corny. I do stand-up comedy, but it's not very good. No one ever shows up, so there you go. Okay, but I'm not drawing sympathy. I'm an optimist. I told you that. All right. So we've talked about quadratics in some detail before. Believe it or not, you remember that a quadratic in one variable is defined. It's an x squared function, but there has to be other certain behaviors. Ax squared plus bx plus c where a, b, and c are real numbers. These are the coefficients of it. Now that means they could be 0. If c was 0, you wouldn't even see a constant here, but it's still there in spirit as 0. What makes this a quadratic is that the leading term is x squared and nothing else behaves poorly. There's no square root of x. That completely screws everything up. That destroys it. So it's a second degree polynomial. When we graph these, you probably already know, we end up with what are called parabolas. So let us see my attempt at a parabola. I have to draw this one freehand. And I'm not looking forward to it, but there's going to be 2 principal forms that a parabola can take. And look, that's as good as it gets. You're just going to have to accept that. And that almost looks like a smiling kitty or something. I don't know, something weird. but there's only two forms it could take. What we call a smiling parabola, and that is kind of the official term for it. Because what better than to say that's just smiling? It's pointing up at both ends. In other words, it's going to positive infinity this direction and positive infinity this direction. So then the other type of parabola must be a frowning one. And yeah, that's exactly correct. It'll look something like this. I don't know, maybe. And of course, they can achieve this all kinds of ways. It doesn't have to cross the x-axis at all. It can go like that. Or it can come up here, or here, or here. So we're just talking about the general shapes here. Don't think that every frowning parabola has to look exactly like this. And remember, there's all kinds of things you can do. You can squeeze it, or compress it horizontally so it looks like that. Or you can even stretch it horizontally, something like that. There's all kinds of ways you can change it. So we're just talking general shape here. So this is a smiling, not a smling, a smiling parabola. This is produced when the coefficient of the x squared term, in other words, when a is a positive number. That's how you get a smiling parabola. It doesn't matter what these two guys are doing, the B or the C. They can be anything on the planet. Now, they may affect the shape or the position of the parabola on the graph, but they do not affect whether it's smiling or frowning. A frowning parabola, then, that occurs just like you'd think when the coefficient of the x squared term is negative, when it's less than 0, which is a great Bret Easton Ellis novel. When a is less than 0, you get a frowning parabola. Again, doesn't matter what these two are doing, what B, X, and C are doing, that will not affect whether it's frowning or not. That is strictly decided by the A. And now you might be saying, well, what about when A is exactly equal to 0? Well, then you don't have a parabola, because if A is 0, the x squared term goes away completely. So you're not even talking a parabola at this point. So sometimes you'll also see another definition of a quadratic as it looks like this, and A shouldn't be 0. If it is, you're dealing with something else. This is the key feature of a quadratic. Okay, so we've got smiling, we've got frowning, we can move them all about. I will move this one slightly and say, oh, I can go over here, you can do all kinds of things. But another key point to pay attention to, another key idea, concept, is that whenever you have a parabola, if it's a smiling parabola pointing upwards, that means it's going to have a point where it just bottoms out. It bottoms out. This is called a minimum. It's the minimum value. It's the lowest point. If you have a frowning parabola, you're going to have a point where it tops out. It's high point, if you will. But no matter what, either of these points is called the vertex. It's called the vertex. It's either the highest or lowest point on the quadratic, depending on what you have. What's interesting is that a smiling parabola has a lowest point, but no highest point, because this keeps going and going and going and going and going forever and ever. It trails off to positive infinity on along the y-axis. So there is no highest point. This says the opposite thing. There is a highest point for a frowning parabola, but these trail off down, 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 down to negative infinity. So that's kind of interesting. What we're also going to define is points where our graphs cross the x-axis, but sometimes they may not cross the x-axis perfectly, and I'll show you what I mean. But there's a couple words for those. So look, boom, it crosses the x-axis there. This one crosses the x-axis here. And these two things, and unfortunately there's just not a good way to draw this without it looking like John Madden type. Either way you want to call them, sometimes they're called zeros. Not because the x value is 0, but because they produce a y value of 0. So you might say right here, this x value could be positive 1. It's 1 on the x-axis. And if I plug it in, it produces a 0 for y. It spits out a 0. So it's called a 0, but it may not be x equals 0 itself. That's why I kind of don't love this word for it. I like to use the word roots. Roots. I think there's another word for it, but I don't remember off the top of my head. Zeros or roots. I usually like the term roots. It's where this thing is planted, if you will, along the x-axis. So that's why you might see it called roots. So this particular parabola as drawn has 2 roots. It crosses the x-axis twice. What's cool is that there's something called the the fundamental theorem of algebra. And if it's fundamental, it's probably pretty important, and it is. For a polynomial, the highest power you see, the degree of the polynomial, tells you the most number of times this thing could cross the x-axis when graphed. All quadratics need to have an x squared, so the highest power is 2. So the most number of times a quadratic could possibly cross the x-axis is twice. It can never do it more than twice. And if you think about just the geometry of it, I'll come play around with this one. Yeah, there's no way to get it to touch more than twice. You can do this, you can try to mess it around. If you kept going and you imagine the parabola was still being drawn underneath it, it's still only going to touch twice. It is possible that it touches just one time. So the fundamental theorem just says the maximum number of times it can touch the x-axis or cross it is the degree, the highest power, which is 2. It's not saying it will touch it that many times. You can always come in under that. In fact, this one does just that. It doesn't even cross the x-axis. It only just barely touches it. I'll make a nice big point there. So then this just has a single root. There's only one root, only 1 0 to this. That's okay. There's nothing wrong with that. It's also even possible that this thing doesn't even touch the x-axis at all. It never crosses it. Look at that. The highest point is yet below the x-axis. This will never touch that. This thing will have no roots. That's okay. You may remember when we dealt with the quadratic formula, negative b plus or minus the square root of b squared minus 4ac all over 2a. You might remember that when we dealt with the quadratic formula, we looked at the business inside the square root, the b squared minus 4ac. We called that the discriminant. That wasn't just some random word we thought of that sounds confusing. It's called the discriminant because it discriminates between the types of solutions that a quadratic can have. If the discriminant is positive, you're going to have this situation where when you graph the parabola, it's going to cross the x-axis 2 times at 2 different points. In fact, the zeros or the roots are actually just the solutions to a quadratic. When you set it equal to 0, you factor it or do whatever, and you solve it. Whatever x values you get when you solve it are exactly the x values that it's going to cross the x-axis at. That is the key here. Because think about it, you set the quadratic equal to 0, you're trying to find what x values produce a y value of 0, which is exactly what it means to cross the x-axis. Those are x values for which y is 0. The y coordinate on these 2 points would be 0 over here. So it's all kind of connecting. The discriminant also says, well, if you get a discriminant of exactly 0, you get a discriminant that is exactly 0. That's going to be that situation here where it just crosses the x-axis. It doesn't technically cross it, it just touches it at one single point. So there's still a solution, but there's only one of them, which kind of makes sense because the discriminant is inside that thing that's being plus or minus. If you're doing plus or minus 0, you're not doing two different solutions. You're only going to have one. But that's kind of behind the scenes. And then finally, if you get a discriminant that is negative, you're trying to take the square root of a negative number, which brings I into the mix. I is inherently not going to be a real number. Since graphs are only meant to be of real numbers, the x-axis is all real numbers, the y-axis has all real numbers, and you're trying to say your roots, your solutions are not real numbers, it can't possibly touch the x-axis. It doesn't make sense. So this third case is where that discriminant is negative. Whew, let's pause for a moment. Let's take a little breath. This is a lot. This is a lot going on here. So make no bones, this is, we're covering a lot of ground. Now, maybe you've seen this before, maybe you use it, have used it, seen it in previous algebra classes. I would assume you have, which is good. Now, let's simplify our lives here just a wee bit, and let's get back to talking about this vertex. This vertex. The vertex is a point on the parabola. Good reasoning, yeah, that's exactly what it is. It's a point. It's a low point for a smiling parabola, the high point for a frowning parabola. Every point, at least if you just have your two variables x and y, has an x coordinate and a y coordinate. Okay, so far nothing new, nothing should be surprising you here. There is a simple formula to find the vertex, or excuse me, to find the x coordinate of the vertex. This is what it's going to be. X equals, it's going to involve A, B, and actually not C, but it's going to involve the coefficients of the original quadratic you're dealing with. It's going to involve those coefficients. It's going to be negative B over 2 times A. Let me draw a better A than that. Negative B over 2A. That will be the x coordinate of the vertex. We'll do a couple examples here using some different quadratics. Now, to find the y coordinate, because the vertex is a point, it's got an x and a y coordinate. To find the y coordinate of the vertex. Well, wait a minute. I always find a y coordinate by taking whichever x coordinate I want and plugging it into the function. So to find the y coordinate of the vertex, plug the x coordinate into the function. All right, so lots of stuff coming at you here. Lots of stuff coming at you here. Let's take a moment. Let's wipe the screen. Breathe for a second. All right, let's try this out. Let's find the vertex of let's give you a function here. How about, let me think of something that would be interesting. All right, so we've got 18x plus 7 minus 3x squared. So what I'm going to do is I'm going to do this the wrong way. Well, and I'm going to use my surfer dude voice. Secretly, it's actually my frat guy voice, but I call it my surfer dude voice. Don't ask me why. Well, like, all right, here's what's going on. Like, that's the first number I see, so that's like A, and that's like B, and this is like C. All right, it's easy as A, B, C. Oh, all right. And now I'm gonna do my x equals negative b over 2a. All right. And so like b is 7, so it's like negative 7 over like 2 times like what a is 18. Well, actually, assuming that we had the right a, b, and c, we did this process right, but we did not do this process right. Just because it's written out of order, we always like to have the x squared term going first. Just because it's written out of order doesn't matter. It doesn't change the nature of that quadratic. So what we ought to do is put it in order. But no matter what, a is always the coefficient of the x squared term. B is always the coefficient of the x term. C is always the constant, no matter what order they're thrown at you. So in reality, for our own sake, I'll rearrange the terms. And I'm allowed to do that because of the commutative property of addition. I'm allowed to do that. I'm gonna need a little more space than that. 2 plus 3 is equal to 3 plus 2, so I can rearrange these at my whim. There we go. And now what we'll see is, wait a minute, actually this is A. Negative 3. This is B, 18. And then this is C, 7. And then I'll clean this up a little bit. So negative b over 2a, so it's going to be negative whatever we have. Since it's positive 18, it's going to be negative 18 over 2 times a is negative 3. That's the right way to do it. That's going to give us the x coordinate of our vertex here. So we just clean up the math a little bit. Negative 18 on top. 2 times negative 3 is negative 6. Those will become positive. 18 divided by 6 is 3. So over here, the vertex, which is a coordinate, it's going to have an x coordinate of 3. That was the whole song and dance with this. But always a y coordinate there is. You're not done. The vertex is not 3. The vertex is a point. So I need the y coordinate as well. How am I going to get it? Well, any y coordinate I want on the planet, I take an x coordinate and plug it into the function. So now I've got to find f of 3. I got to plug a 3 into the function. Might have a little bit of math to do. Following order of operations. According to order of operations, I'm going to have to do the 3 squared first. No, you're not going to just plug this into a calculator. That's not how it flies in this class. Then we got to do 18 times 3 if you can't do that in your head, which is totally fine. I usually can't do that kind of stuff in my head. You can do old school. 3 times 18, 3 times 8 rather is 24, carry that through the 54. So that's going to become plus 54 plus 7. And then we got to just kind of clean up, do the arithmetic. Negative 3 times 9, negative 27, plus 54, plus 7. Gosh, I guess we can do the 54 plus 7 first. Because now, well, let's do it left to right. Just because that's technically proper, but it would have worked out either way. Now we got to do negative 27 plus 54, which is the same as 54 minus 27. You're going to get 27 out of that. So you're going to get positive 27 plus 7, which maybe you can see will be 34. Oops. So that's going to be our y coordinate here. And now we're done. So we've got the vertex as 3, 34. Let's do a simple graph of this. It's not going to be a fully detailed graph. We're going to do a simple low down version of this, where all I'm going to do is label the vertex, and all I'm going to do is make it either a frowning or a smiling graph. All right. I don't know, something like that. So because a is a negative number, negative 3, this is going to be a frowning parabola. It's going to have a vertex of 3, 34. So I'll put that maybe right here. It's going to be frowning. And maybe we'll give it ghost eyes, a smile. That doesn't really look like a ghost. That just looks like you draw like a finger puppet, like you draw on your finger. So that's the extent of my artistic ability. And so right there, I'm going to make a nice big fat point. That's going to be the vertex, the point 3, 34. And we know it's frowning because a is negative. So this is more of a sketch of the graph. It's not super detailed because I actually didn't finish off the process and figure out where it's going to cross the x-axis. But here's some good news. Knowing that the vertex, the y-coordinate, is above the x-axis, is positive up here, and it's frowning, that automatically implies that it's going to cross the x-axis twice. If this had been 3, negative 34, and still frowning, I would know that the whole thing, oops, I don't want that. I would know that the whole thing comes crashing down below the x-axis if this was 3, negative 34. And since it's still frowning, I would also know it doesn't have any roots. So there you go. If I had known if the vertex had a y-coordinate of 0, I would know this is that case where it touches the x-axis just once and only has one root. I would know that. But instead, I know the vertex is positive, the y-coordinate is positive, and it's got to be frowning. So I know there's going to be 2 distinct roots here. That's pretty cool. And you can eyeball that without even drawing the graph. You can kind of just see the geometry in your mind. Okay, so we're at that uncomfortable moment where there's about 4 minutes left, and I don't want to start on the next thing because it takes about 10 minutes to go through. Chapter 3 is not even on your exam next week. Chapter 3 is not, but I wanted to give you a little introduction to it just because we have the time. We'll be reviewing on Tuesday. I've got a little over 3 minutes I have to fill. So what I'm going to do, I am going to talk very slowly and
Oh,
keep.
I'm bad. I'm bad.
What's that?
Not you.
Oh, no. So yeah, we've got a couple minutes, and yeah, you guys are free to ask me any questions. I'll tell you no lies. We'll be reviewing Tuesday. Are you guys seeing everything showing up properly on MyLabs Plus?